Without further ado, we welcome back Alex Martsinkovsky for stabilization and additive functors too. But we don't assume we know the first one. Go.
Well, don't assume we remember.
Yes, and you should not assume that I remember. Right, thank you very much. It's very nice to be back. As Nelson said, we met here last December. I was here for a propaganda talk, and today propaganda continues. So the plan of today's talk is, well, we again review generalities on derived functors. We'll review what it means to stabilize additive functors. And after that, so where's the propaganda part? I will try and show that this notion of stabilization allows you to redefine the notion of torsion. So I will give you precise details as we come to that. And more amazingly, it leads to a notion of cotorsion. If you do the search on cotorsion on MathSciNet, you will get more than 600 entries. So I claim none of them is the cotorsion that it should be. And I will try and make it clear during the talk. So that's part 4. So one of the reasons why I'm treating this so arrogantly is that there's a good formalism behind torsion and cotorsion. They're related by a certain machinery, abstract machinery. It's another kind of functor, and you can go back and forth between torsion and cotorsion. So historically, this path was traversed by some kind of mathematical argument. But then this Auslander-Gruson-Jensen functor actually affects and turns mathematical philosophical arguments into solid mathematical arguments. And in the end, I will. That much I was about to speak back in December. And then I added one more thing that's a major development over the summer month, that now we can compute the derived functors of both torsion and cotorsion. Certain restrictions on the ring are required, but in particular we will be able to compute these derived functors for example, for modules or arbitrary finite dimensional algebras, or even Artin algebras. So it's a very large class. Okay, so let's talk about derived functors. So today all functors will start from modules and go into abelian groups. Moreover, we assume that the functors are additive. If you have a module, you can take a projective mapping onto it, look at the kernel, map another projective onto the kernel, and continue indefinitely. Sometimes you stop, sometimes you have to go to infinity, whatever it is. This part of the sequence, beginning with P0 and extending to the left, is called the projective resolution. There's nothing unique about it, except that the homotopy type of this complex is uniquely determined. Likewise, start with a module M. You can embed it into an injective container, take the core kernel, embed it into another injective container, and continue going on. And this way you get what is known as an injective resolution. Nothing unique about that either. But again, any two injective resolutions are homotopy equivalent. So why is the homotopy equivalence important? That means that if you apply an additive functor, then the resulting homology group will be uniquely determined because of the homotopy uniqueness. And that gives us the so-called derived functors. Here you see a table, the left derived functors denoted by Li, f. The right derived functor is denoted by Ri, f. It is convenient to separate the covariant-contravariant case. And in the contravariant case, we flipped the superscripts and subscripts. Normally in the literature you see the superscript for a right derived functor. In the contravariant case, we use the subscript. And likewise for the left derived functors.
I'm sorry, I understand projective resolution. How is Li defined as opposed to Ri?
Well, the table contains an answer to this. So if you want Li and the functor is covariant, you take a projective resolution. This is the word that tells you which resolution to take. That defines Li. If you want to Li in the contravariant case, you take an injective resolution. Because F
could be injective.
Will flip the resolution from the right, where the injectives live, over to the left. So it is the endpoint designation that tells you whether it's left or a right.
Okay.
Well, here's the table which mentions the case I equals 0, the zeros derived functor. People have no respect for the zeros derived functor. Why? Because they had been brainwashed that the zeros derived functor of home is home and the zeros derived functor of tor is tor. It's not always true. You have to be aware that the zeroth left derived functor, the right derived functor of home is indeed home, but what happens if you take the left derived functor of home? Have you ever taken the left derived functor of home? I bet you haven't. Few people have ever tried to do that. And that's a pity because this operation really explores something really fundamental. So I'll try and convince you that you can get a lot of interesting information from that zeros derived functor. Here's another phenomenon that appears in degree 0 only. If the degree 0 functor and the functor itself are not isomorphic, well, at least there are maps or natural transformations between them in all the 4 cases. And classically, in all the textbooks on homological algebra, you will see that this transformation is an isomorphism if and only if f is right exact. That everybody knows. But what if it's not right exact? And it's not an isomorphism. So what is it? Likewise for the remaining 3 cells. The situation is aggravated by a comment by Carton and Eilenberg, who say that it's only of interest to compute the derived functors of functors which are either left exact or right exact. Of course, this is true, because the high derived functors of such functors coincide, well, of any functor. For any functor, the high derived functor of this functor and its zeros derived functor are the same thing. But that bypasses the question of what is the zeros derived functor. So today we will be looking into that question. So why is this case so interesting? Not only because we have extra creatures in this table, but also the arrows, these natural transformations that appear there, they are universal. So these are some kind of approximations. So you should view this arrow as an approximation of an arbitrary functor with a right exact functor. Similar here. Here's an approximation of your functor with a left exact functor. Likewise here. And what does that mean precisely? Well, here's the picture. Here's your transformation from the 0th left derived functor, that's right exact, and it goes to f. If you take any right exact functor and send it to f, it turns out that it lifts over lambda sub f in a unique way.
Is this a Kahn extension? Is this a Kahn lifting?
Well, this is definitely a co-reflective. Well, here's what it is. If you look at the subcategory of all right exact functors in the category of all functors, then this category is co-reflective, and lambda is the co-unit of the adjunction. A similar statement applies to left exact functors. In this case, the subcategory of all left exact functors is reflective in the category of functors. There's more to this picture. Turns out that when you evaluate this natural transformation on projectives, in the case of a covariant functor, it's an isomorphism. If the functor is contravariant, then it's an isomorphism on injectives. And here comes another uniqueness. Namely, this, by the way, some authors call this whole transformation the 0th derived functor. Not just this part, but this whole transformation. And the uniqueness property I just mentioned a moment ago says that this is the unique natural, this is the unique natural transformation from a right exact functor to f that evaluates to an isomorphism on projectives. In the contravariant case, on injectives. Here's a similar statement for the right derived functor. It's an isomorphism on injectives for covariant functors and projectives in the contravariant case. And again, that's a unique natural transformation. Use this property. A unique natural transformation to a left exact functor. Here's an example. I'm going to look at the old friend of ours, the covariant home functor. So A is just a label. We fix that module. Take home from A to anything we like. So I have to assume that A is finitely generated. In this case, this transformation, this canonical transformation, is simply the map that you encounter in any textbook on linear algebra. If you have a vector here and the linear form there, what can you do? Give me another vector. You can evaluate the linear form on that vector and use the scalar to scale that vector. So this gives you a vector here. So in all elementary texts on linear algebra, you can see this map. So what is it? Well, it's an isomorphism on projectives. Well, how do you prove this? You look at what happens when you evaluate on the ring. Well, it's A star going to A star. So that should be an isomorphism. It's easy to check if you write down what this map is. Therefore, it's an isomorphism on finitely generated projectives. In fact, on finitely generated free modules. In fact, it's an isomorphism on all free modules. Why? Because that's where the assumption on A being finitely generated kicks in. If this is the case, then you can take an arbitrary direct sum here and pull it out. So this isomorphism in lambda implies the isomorphism on any free module. And if it's an isomorphism on any free module, then it's an isomorphism on any projective, which is a direct sine of free. So therefore, by our criterion, this must be the zeroth left derived functor. It's right exactly apparently because it's a tensor product. This transformation is an isomorphism on projectives. So if this is the zeroth derived functor, then you know all other derived functors because the derived functor of a functor is the same thing as a derived functor with zeroth derived functor. The zeroth derived functor is a tensor product, so its derived functors are tor I. So here's what you can take home. The left zeroth derived functor of the covariant Hom functor is tor. Not quite. Tor with some twist right here. You're accustomed to the statement that the zeroth left derived functor of the Hom functor. Well, we don't know what it is, but now you do. Normally you take the right derived functors. These are x's. The left derived functors will be tors with some twist. And a similar argument applies to the tensor product. Here you have to work a little bit more, not much though. So this is your functor, tensor product with a fixed module with anything you like. We need to construct the transformation rho. I should have written rho sub f actually. It's not nice to write it without the subscript. Well, again, this is a linear transformation you can find in any textbook on linear. So if you have a vector and another vector and a linear form, take that linear form, evaluate it in the vector here, and scale the vector to the half here. So you get a vector in this way. So you get a map from A star into anything you like. And you can show that this is an isomorphism on injectives, provided we have this assumption that A, B finitely presented. It's not as immediate as it used to be in the previous example, but it's still fairly easy to show. As a consequence, the right derived functors of the tensor product will be the x functors with a twist again. Okay. So I am almost through in my history of the world in 3 minutes flat. So let's discuss the main technical tool, the stabilization of additive functors. Back to this table. So what are we seeing here? Same creatures. The transformations between functors and their derived functors. Except we now have new characters, these letters P and I. Well, if this is the value of the, what is it, co-unit of a junction, take the co-kernel. And the resulting functor will be called the projective stabilization of the functor F. Likewise here in the conjugate case. If this is the unit, the value of the unit of a junction rho on F, take the kernel. The resulting functor is called the injective stabilization of the functor F. So this is very easy to remember. Never try to remember this using covariant, contravariant, projective, injective resolutions. You get lost immediately. The easy way is to take the co-kernel of the co-unit and take the kernel of the unit. That's where you immediately remember. I forgot, is T being served during the seminar?
No.
No?
No. No, we go to LP afterwards.
Okay.
And they get this order.
Okay. So let's concentrate on the injective stabilization of an additive function. We know what it is. That's the kernel of this canonical transformation from the functorial zeros right to right functor. Well, here's the standard notation for it. F upper bar. It's an additive functor, so we are not living our universe of additive functors. It's a subfunctor of an additive functor. How do you actually compute it? There's no general recipe. Well, actually there is. What do you need to do? Suppose you want to compute the component of this injective stabilization. 3 steps you need to follow is the following. You embed your module B in an injective. So you take an injective container for the module B. So you have this embedding. Apply your functor F to this embedding. And then compute the kernel of the result. It's no longer a monomorphism anymore. Why shouldn't it? So here's the defining sequence. So if you want to compute the injective stabilization of the functor F on the module B, just follow this procedure. B into I, apply the functor and take the kernel. It's interesting for one simple reason. When you speak of the, remember, the definition of the zeros derived functor tells you to take the homology in degree 0. For this, you need to know what you have in degree 0 and in degree 1. So you may think that you need to do 2 steps into the resolution to compute this and then compute F bar. No, it's enough to take just 1 step. Just embed B into 1 single injective, and that's already enough. So we're going to concentrate on the injective stabilization of the tensor product. In this case, we have to modify the notation. Here's the reason why. So if you look back, we see that F bar is a subfunctor of F, always. So this A harpoon B, which is our notation for the injective stabilization of the functor A tensor blank on B, has this interesting new symbol. We don't use the overbar anymore. Why? Unlike this ambient functor, the tensor product, which is exact, you know, to compute tor I A B, you can take a projective resolution of A, or you can take a projective resolution of B. The result will be the same. This property is referred to as being balanced. So the tor functor is balanced. However, the injective stabilization of the tensor product is highly unbalanced. So you need to remember where you took your injective resolution. On the left or on the right. So here's an example. So we're talking about abelian groups, Z modules. So we're going to compute the injective stabilization of Z tensor blank. I computed on Q mod Z. What is it? Well, that's clearly 0 because Q mod Z is injective, so its injective resolution will be an isomorphism of Q of Z with itself. When you apply any functor to it, it's still an isomorphism, so you won't get any kernel. Alternatively, you can say, oh, I'm tensoring with Z, it's a projective module. It preserves monomorphisms. So this kernel will be 0. But if you now take the injective resolution of Z and tensor with Q mod Z, what will you get? Well, here's the injective resolution of Z, tensor with Q mod Z, what happens? Well, z with q mod z will give you q mod z, but this part, well, q will kill q mod z. So you're left with q mod z. So what's the normal here? Well, I told you that this injective stabilization is a subfunction of the tensor product. In this case, the tensor product will be z with q mod z, which is q mod z. And yet we have two different outcomes. 0 on one side, q mod z on the other. And you see, the difference could be pretty dramatic, as large as possible. This is the smallest possible outcome, this is the largest possible outcome. So remember, this is not a balanced functor, so this arrow that points, the harpoon that points to the active variable is absolutely necessary if you want to keep track of what you're doing. In fact, it can be computed in terms of homological functors. So this was done 50 years ago by Auslander. The creature that stands here is called a transpose. So this is all done under the assumption that A is finitely presented. If you have a finitely presented module, that means you can find a finite presentation. So these are finitely generated projectives. If you like, you can take finitely generated free modules. And then upon dualization, say, assume these are free modules. And this is the matrix of say, M. When you dualize, you get this part for free. These PI star are still free modules. But what you do now is you take the core kernel of this map, and that is the definition of the transpose of A. And the name is derived from the fact that if the matrix of this map is M, then the matrix of this dual map will be the transpose of M. Where's the name? And that's what goes away. What's the projective stabilization of the covariant home? In the previous picture, we saw the injective stabilization of the tensor product. I only know three functors: the tensor product and two homes, covariant, contravariant. And I can make a case you don't need to know anything else. So, what's the stabilization? How about projective stabilization of the covariant home? Well, that's just home modular projectives. So you just take home and you mod out all the maps that factors through projective modules. And again, there's a formula. Tor1 of that same transpose that I mentioned before. Here again, you have to assume that A is finitely presented.
So trace of A is like that A star?
The transpose? Yeah, transpose is literally the core kernel of the transposed matrix.
But before you had A comma, you had an isomorphism. A, yeah, okay, fine, don't go back. Yeah. Okay, fine.
Yeah. There's a certain symmetry here. Well, you may ask, how about the injective stabilization of A comma blank? Don't even try this. Why? Because home is left exact. So you have a module sitting inside its injective envelope, you apply a left exact functor, you still get a monomorphism, so the kernel will be 0. So never try to injectively stabilize the home functor. You will get 0 in the end. Okay. So what else? Well, projective stabilization of contravariant home functor. Here we have a surprise. The projective stabilization of the contravariant home functor is home modular injectives. The projective stabilization of the contravariant home functor is home modular injectives. This is strange. Projective stabilization returns home modular injectives. Okay, good. That's where we were almost a year ago. Any questions? So now I want to define torsion. So what exactly do we want to do? So given any module, I want to define a torsion submodule. You probably saw the definition of torsion for abelian groups or for modules over commutative domains, but I want to extend the definition to arbitrary rings and arbitrary modules. And moreover, I want to define a dual notion of cotorsion, and that should be a quotient module. If you agree that torsion is a submodule, then cotorsion should be a quotient. And that's what is missing in all the existing definition of cotorsion. Cotorsion module should be a quotient module. So give me a module and show me the natural transformation from the identity functor onto something else. Then I can talk to you about cotorsion. If you don't have this transformation, don't call what you get cotorsion. Well, here's an algebraic definition, but the interesting thing is that it has a geometric origin, actually topological. The definition of torsion goes back to the work of Poincaré. So in around 1900, he was working with the cellular or triangular decompositions of manifolds, and he did the following calculation. He, in a certain dimension, he took a cell and wrote down the boundary. So this gives him an incidence matrix. So, and then he brought the matrix to the Smith normal form. Smith's theorem had been proved 40 years before that, so he was aware of this. And then he made a remark. By the way, this is according to Dieudonné from his book on the history of algebraic topology. And then he makes a remark that if on the diagonal I have a number which is greater than 1, then I can construct a cycle which is not a boundary, but a multiple of this is a boundary. So what does that mean? He simply constructs a torsion element in the homology group. And as you see, this is purely topological, or geometric, whatever your favorite word is. Well, here's the...
Did he have the notion of Betty numbers? I mean, this is before homology, so this is...
He had everything at that level. He invented the first month of algebraic topology 100%, except he didn't quite cast it in the form of homomorphisms, but he came darn close. So in the 20s, Emmy Noether and her team went through Poincaré. They realized wherever you could,
you can make a group out of it.
Right, to formally define it without passing to the coordinatization in terms of matrices. It wasn't always necessary. That's as far as I can tell from looking at Poincaré.
So,
I think that's the standard.
But he didn't have a group. He had Betty numbers.
Yeah.
Oh, sure.
Yeah, he had
Betty had,
Yeah, Betty.
Betty Riemann had them.
Yeah. Yeah, he had the full tower of Betty numbers.
Yeah.
I think he had the full month. I don't know what they teach today. I think he had it 100%. He made mistakes, of course. And then he corrected them.
Yes.
It was all new, right? So he would publish, this is the homology. Then 6 months later he'd say, no, I miscalculated. And then he got it right.
So this is the definition of a commutative domain. If you have a module A, the domain is R, then you look at the totality of all elements that are annihilated by non-zero elements of the domain R. It turns out to be a submodule, and it's called a torsion submodule. So that's the classical torsion. I will refer to this as classical torsion, defined by commutative domains. Now, it can be extended to arbitrary rings in more than one way, but today I want to simultaneously generalize a different notion due to Bass. So let's call it Bass torsion. So what is it? Bass gave a completely different approach to the notion of torsion. He looked, for any module, he looked at the canonical map from a module to its bidual. And looked at the kernel of this. So here's the defining sequence of what we call the Bass torsion.
I'm sorry, isn't A into A double star, isn't that an isomorphism?
No, not really. For example, if A is torsion, then A star is 0, and A double star is 0. So it cannot be an isomorphism. For vector spaces, it is. For finite-dimensional vector spaces, right?
Okay, so that's what they're talking, okay, fine, sorry.
Yeah, for finite-dimensional vector spaces, it is. But for infinite-dimensional vector spaces, already it's not an isomorphism, because the cardinality of the double dual, of the dual array will be bigger than the cardinality of the original vector space. Very well. So notice that it is defined, this map is canonical, defined for any module over any ring, and it has a nice description. So what's the kernel of this map? It's precisely the set of the subset of all elements on which every linear formula vanishes. It's straight from the definition. And why is this important? What does it have to do with torsion? If R happens to be a commutative domain, and A is also finally generated, then the classical torsion, I call, denoted by capital T of A, coincides with the Bass torsion. That's a totally different description. So this Bass torsion could be quite big. Why? Well, again, let's go back to integers and take the additive group of the rational numbers. So what is Q dual? Well, Q is a divisible abelian group. You cannot map it into Z. So Q star is already 0. Q double star is 0. So the kernel of the map from Q to its bidual will be the whole Q. But everybody knows that classically, so T of Q is the whole Q, but classically Q has no torsion. There are no torsion elements.
So classical torsion injects into Bass torsion? Is that true?
Yes. How did you know?
Yeah.
That's a theorem. Yes.
What does star mean?
It's dual with respect to the ring. So you take it's like the dual vector space.
But, so just finite?
Not necessarily.
No, okay.
You have for any module.
All linear maps down
That's
to the scalars?
Yes. So
Okay,
M
thanks.
star is just, sorry,
Right.
I've been used to this notation for,
Well,
used it for so many years.
Right.
I forget to mention. This is home
yes.
over the ring, move from the module to the ring.
Okay, just checking.
Yes.
Thank you.
Yes.
If you have a topology, of course, then you get different stuff.
Okay. Now, Bass torsion is actually more interesting than classical torsion. It appears in many different contexts. There's no time for me to explain all the occurrences, and also I don't know some of the stuff here that I mentioned.
Ah.
But it appears as far from algebra as linear control systems and partial differential equations. The amazing thing is, and it was really a revelation to me, that stable module theory was done by Auslander-Gruson in the late 60s. Independently, people from differential equations did similar things. They didn't know about Auslander, and Auslander didn't know about them. And amazingly, very few people are aware of this parallelism. I know of maybe 3, 4, 5 people who are aware of this fact, that there has been parallel work. Anyway, personally, I love Bayes torsion, so I would like to keep it. And here's the problem. I want to simultaneously generalize the classical torsion and the Bayes torsion. Bayes torsion has been used for, in which context? In all of those contexts, the modules were finitely generated over Noetherian rings. So what it actually means is that all the modules inside were finitely presented. So okay, I'm happy with that. So I want to simultaneously generalize the classical torsion for arbitrary modules over commutative domains, and Bayes torsion for finitely presented modules, but over arbitrary rings. And that should work for arbitrary modules over arbitrary rings. So the definition should be in complete generality. How can this be done? Well, let's take a look at the classical torsion via localization. Here R is again the commutative domain. It embeds into its field of fraction the same way that rationals, integers embed into rationals. Okay, what is it? Well, that's a localization map. From the ring to the localized ring. In this case, the localized ring is a field. Well, you can tensor it with a module, and that will do the same thing for the module. You tensor it with the module A. Tensor this map with the module A. So you start with A, and that goes to A tensor K. And that's a localization map for the module A. And the striking fact here is that the classical torsion is precisely the kernel of this map. And this is one of the first exercises you do when you study localization. But let's make a crucial observation. So who is R? It's just the ring, viewed as a module. Who is K? The quotient field. But actually it's an injective envelope.
Okay, sorry. What's an injective envelope?
It's an injective container. It's an injective module that contains your module.
Okay.
And the injective envelope is the smallest one of all those. That's all. But your question is right to the point, because it doesn't matter whether it's an injective envelope or not. All I need to know is that this is an injective container, something that contains it. I already mentioned these words 10 minutes ago. Take a module, embed it into an injective container, and apply your functor. Well, that's exactly what we're doing here. We took a module, we took something, embedded it into K, and then applied the tensor product.
The point is A tensor K has no torsion because it's a field. And
it's
so
a vector space.
it's a vector space. Well, K is a field.
K is a field.
A tensor K is a, and so you're mapping everything, and you want to know what goes to 0.
Yeah,
okay,
exactly.
Because there is no torsion on the right. There's no.
Yes. So, that to me, that sounds like computing the injective stabilization.
Rational homotopy theory. No, I mean that's what they do. That's the trick that they do. They look at coefficients in a field.
That's exactly what the injective stabilization does. So what do you do? take a module, embed it into an injective module, apply the functor and take the kernel. That's what we're doing here. And that motivates the new definition. So now we are living the universe of commutative domains. Our rings could be non-commutative, so we have to, since we will be taking a tensor product, there will be a left module and there will be a right module. So let's look at lambda as a right module. Embedded into an injective container, doesn't have to be an injective envelope. Okay. And what do you do next? Well, apply the functor A tensor blank and take the kernel. And this will be our new definition of torsion. S of A is the kernel of A tensor lambda going into A tensor I. So what happened here? Our functor is A tensor blank, and we took the injective stabilization of this functor, evaluated at lambda. We took lambda, embedded into an injective envelope, applied the functor, and took the kernel. It's very simple. So, by design, we immediately have that the new torsion coincides with classical torsion in the commutative, in the case of a commutative domain.
That's the first thing I've actually understood.
Thank you. I view this as a compliment because that's the only thing that people need to understand.
Okay, I don't know it much.
If you understand what that is, then you already understand the importance of the injective stabilization. It turns out, and it's a theorem, maybe a proposition, or even lemma, or just an observation, that on finally presented modules, it coincides with the best torsion. So we are done. It requires a proof, but the proof is not difficult. It's in the papers. It's just take a few lines. Not very difficult. So we have found a common generalization of classical torsion and best torsion. So, awesome.
Yeah.
Somehow you were able to read the first line here 10 minutes ago, before you showed it. There's this new torsion always sits inside the best torsion.
Nice.
Yeah. Well, that has preserves field of colimits. That's another thing. That's the reason for this is because it's defined through tensor products, and tensor products have this property. Turns out that this S is the largest subfunctor of T that preserves filter colimits.
That's good.
And that tells you what's wrong with the best torsion.
Yeah.
In general, it doesn't preserve filter colimits. Otherwise, Q would still have torsion 0, best torsion 0, but it doesn't. Another nice property of S is that it's a radical. So if you mod out the torsion and you attempt to take the torsion again, you get 0.
Nice.
And for flat modules, well, because tensoring with flats is an exact functor, the torsion of any flat module is 0.
Well, go back for 1 second.
Sure.
Let's say you did this for classical torsion. I mean, you did that radical trick. Wouldn't it also be 0?
This is true for any module or any ring, yes.
But for... okay.
What bothers you?
Well, he's asking if you have the same property for the other definitions of torsion. Or can you give an example where it fails?
Yes. For best torsion, it's very simple to show. And for classical torsion, it's almost obvious.
Oh, so they're both. It's true in both of them.
Yes.
Mm-hmm.
True. Here we need a proof. And here we use the fact that S preserves filtered colimits. The trick here is to represent a module as a filtered colimit of finally presented modules.
No. So there's a whole class of things that are going to be radicals, and this is taking out a particular one.
A lot of radicals, yes. This is the defining property of the radical. So a pre-radical is just an arbitrary subfunctor of the identity functor. And it is called a radical if it has this property. Well, so when is it zero identically? If and only if it preserves epimorphisms. So any module can be covered by a projective. Projective don't have torsion. So if it preserves epimorphism, then zero would map into the torsion. So the torsion of any module has to be zero. No way out of this. Well, these are technical terms from ring theory. I don't need to discuss them. But here we have a very interesting consequence. Quite often, people with all kinds of torsion, people are trying to answer this question. Under certain conditions, torsion splits off as a direct sum. For example, torsion in abelian groups always splits off as a direct summand. The question here is, does it split off functorially? And the answer for abelian groups is no, doesn't. I guess you can find examples of this in textbooks. I think I've seen one example in Doid's lectures on algebraic topology, for example. There's a chapter on functors there. But here we can prove much more, that the torsion can never split off functorially for any ring. You see, this result, I believe, is new even for commutative domains. And why is that? The proof is essentially one line. Why? Well, suppose S, which is a subfunctor of the identity functor, splits off functorially, then it becomes a quotient functor of the identity functor. The identity functor preserves epimorphisms, so the quotient functor will preserve epimorphisms. And what happens if S preserves epimorphisms? Well, look here. If S preserves epimorphisms, S is zero. That's all. So there cannot be any functorial splitting off of the torsion over any ring, at least for our torsion. So I'm curious if that can actually be used in other contexts. We know, for example, that the commutative relations don't split off functorially. There could be examples. I wonder if one can show that they can never split off functorially. So this is an argument. Maybe this can be used as a blueprint for other contexts. So, and other torsions, other torsion radicals. Very well. Cotorsion, what is it? Well, let's answer a simple question. Why is the torsion a subset of the module A? The reason is due to the fact that we have a canonical isomorphism. Remember, the torsion was a subset of this, A tensor lambda. But A tensor lambda is canonically isomorphic to A, so the torsion is a subset of A. And then immediately we start thinking, oh, is there a dual canonical isomorphism? Of course there is. Home from the ring into any module is the module itself. Everybody knows that, since the kindergarten days. And if you didn't go to kindergarten, you still know it in this segment, because that's just, what is it? That's just Unada's lemma. For the ring viewed as the category with one object. Okay, well, if we took for torsion the injective stabilization of the tensor product, dually we should take the projective stabilization of the countervariant confounded. I am sweeping under the rug a lot of interesting details, and it wasn't as straightforward and easy to guess, but eventually that's what it is. And here's the definition. What is it? We know that the projective stabilization of the countervariant Hom functor is homodular injectives. And where do we evaluate it? On Auslander. Here's the definition of Q. That's just homodular projectives of lambda canonical. And that's a quotient of the identity functor. You mod out all the maps that factor through injectives from the identity functor. Well, I don't think we need to dwell on this. Let me quickly go through the Auslander-Gruson-Jensen formalism. So what you're looking at are two functors D. Don't pay attention to the meaning of the word FP. FP stands for finitely presented. These are finitely presented modules. You see the orientation of modules changes. This is a left module, then this will be right modules, and vice versa. And what does this D do? D does a very simple thing. It interchanges the tensor product with the covariant Hom function. That's all. You can play around, and here's one extension of this from finally presented modules to arbitrary modules. This extension was done by Jeremy what's Dean's name? Sam Dean and Jeremy Russell. Okay. So again, you see a Hom functor.
Does Russell's name end with 2 L's or 1 L?
2.
The bottom line says 1 L.
It says 2, but one got cut off.
No, on the yellow. Yeah.
The
So
yellow.
there's 2 L's, you can only see one.
Oh, I see. That was cut off.
Okay.
Yes. Yeah, I was under duress when I prepared the slides because something happened with the beamer. All this part has disappeared, and I have no idea why. So later complained, TechShop complained that could not process, and I couldn't do anything. And on top of that, I had a problem with my trackpad, so I was desperate. So I didn't really see whether the names fit correctly or not. All right. This functor has 2 adjoints, left and right. Well, Jeremy had this nice picture, and we only need, well now we only need, well, the functor D, and then it's right adjoint. And what do we need to know about it? The first thing is that the functor that goes forward takes the homology injectives and turn it into the injective stabilization of the tensor product. And if you specialize in the case when B equals lambda, that functor, D Russell functor, will take cotorsion and send it to torsion. Don't read this. It's not important at the moment. We can skip this also. And here comes the most interesting thing. If you assume that the injective envelope of the ring is finitely presented, you can go backwards. The right adjoint of the D and Russell functor takes the torsion into cotorsion. So you always can go from cotorsion to torsion, but going back is a challenge. It is overcome if you know that the injective envelope of lambda is finitely presented. So in this case, you can go back and forth. So the two concepts really become dual. For example, in case of a knotting algebra, we know that Q, the cotorsion, can be recovered from torsion. One other thing to take home today, cotorsion behaves better than torsion. It fits, I guess, the general mathematical principle that homology behaves better than homology.
Behaves better means it preserves a monoidal structure or something?
Well, not that far. All I'm saying is that Q determines S, but from S you cannot determine Q. S is a creature that has its own character.
I thought you have functors going both ways, but
Yeah, but they don't necessarily.
one is a co-reflective?
Yeah, well, no, that's here. This tells you that you can always go from Q to S. Always, no matter what. So Q determines S, but S does not determine Q. You can go from S to Q under special conditions. One of them is that the injective envelope of lambda is finally presented. Then you can go backwards from torsion to cotorsion. That's the last line here on the slide. Okay, and finally, let me briefly mention, I think I ran out of time, so let me very briefly go through this new stuff. So first, let's define the FP rings. These FP means finally presented envelope. That's exactly the rings I mentioned a moment ago. So look at the rings whose injective envelope is finitely presented. Okay. All finite dimensional algebras fit in this definition. And you can build a natural transformation from torsion to the Hom functor. So this is the argument here. This is fixed. And what is that label that fixes it? That's the cotorsion of the ring itself. I can tell you what it is. That's the trace of the injective modules. You start mapping all injectives into lambda, and you see what submodule they generate. That's precisely the meaning of that creature, Q of lambda. And there's a map. And what's more is that this map is the zeroth right derived functor. You prove that this map is an isomorphism in injectives, and that gives you the right derived functors of torsion. These are x's of this mysterious creature. You see, cotorsion calls the shots. It determines the derived functors of the torsion. So Q seems to be determining, cotorsion seems to be determining torsion, no the other way around. Now, what about the left derived functors? That's trivial. Projectives don't have torsion, so all derived functors will be zero. So case closed then. And then I'm going to look at another class of ring. It's bigger than the previous one. We only assume that the injective envelope is finitely generated. Well, you always have this natural transformation. Instead of Q, you can have any functor you like. There's always a transformation like this. And this is, under this assumption, this is always an isomorphism with projectives. But we know that that means that this right exact functor must be the zeroth left, the zeroth left derived functor of Q. And the higher derived functors are just the higher derived functors of this. So we have computed the left derived functors of cotorsion. Here they are. And similarly, if you want to go to the right, there's no cotorsion for injective modules, so the right derived functors there all vanish. So we have finished our journey through torsion and cotorsion. This was an illustration how pretty abstract concepts like stabilization of additive functors can bring in some concrete results.
Any questions? I'm a little confused with the adjoint functors, because you have adjoint functors, but if you restrict to finitely presented injective envelopes, then they're equivalents? Is that the point? Then one defines the other? You say that the torsion will define the cotorsion.
Yes, the right adjoint of this Dean-Russell functor
Right.
will bring torsion to cotorsion. So let me repeat it once again.
No, only under that assumption, only under the assumption.
Yep, under that assumption. You, Q, always, if you know Q, you can always recover S?
Yes.
Yes, okay. That's a German S. Okay, if you have Q, you can always recover S. Going backwards is a challenge. You need assumptions.
You need that the injective envelope is projective. That's what you
The
said.
injective envelope is finally presented.
Is finally presented.
That would be enough.
Okay, so if you go on both sides, finally presented injective envelopes, then there would be an equivalence of categories.
Which categories? No, this is not a question about equivalence categories. These are functors. We're only talking about functors. Whether one functor can be recovered from another functor. That's all.
Sorry.
This
yeah.
is not an issue about equivalence of categories.
Sorry. Okay, good. Sorry.
Well, actually, it might be related to the fact that there is an equivalence in this, because this is, in that situation, I think it's the honest Auslander-Gruson-Jensen duality. Because when you have that situation, what happens is the adjoint back is literally the dual that you're used to seeing in model theory. It's the, on the level of finally presented functors on finally presented models. That's what should be happening in that case.
Yes, and maybe I can elaborate on one other aspect very briefly. When we say Q is better than S, Q, in terms of functors, Q is finitely presented. It's a finitely presented functor. You cannot say the same about torsion. So that's another argument in favor of this statement. Q behaves better than S. This is finitely presented. This is, in general, not finitely presented.
Any other questions? Let's thank our speaker again.
Thank you.